Welcome back to Study with Adu. Here is your Adu back once again. Yes, back with the classes of what +2 board examination. So we learned the chapter electric field and charges, electrostatic potential and capacitance. Now the third chapter is current electricity. This is comparatively smaller chapter, but concept wise there are many things to study. Current electricity. Once again, what is electric current? First of all, what is current? Electric current. Normal current means what? There is windy current, etc. The flow of electric charge through a conductor constitutes an electric current. See, current. Very simple. Electric current in a conductor across an area held perpendicular to the direction of flow of charges defined as the amount of it is very simple. What is electric current? Electric current is the amount of charge flowing through a conductor in per unit time, right? Yes. So I can be written as limit, like very short time, t tends to 0, right? Approximately when t tends to 0, the number of charge flowing through a cross section is called as what? Current. That is dq by dt, if you are writing in calculus manner. If the current is constant, that is the current is steady current, that the charge doesn't levitate, then we can write I is equal to q by t. So this is the thing. Okay. Now about this. Now we can also write this thing as we can also write q as integral I dt. This is important. This can be asked. Okay. So these are some equations. Now what is transient current? What is transient current? One second. Yes. What is transient current? It is a current for short time. Current of short duration. Example, what is the example? Lightning and all. 1 second only the lightning will come. After that it will go till what it vanishes. Lightning. Okay. Which is the flow of electric charge due to two clouds or from clouds to earth. Now SI unit of current, this and all is very common, that is ampere. That is A. Now electric current is what? It doesn't have a direction. Electric current is a tensor quantity, but here we don't know what is a tensor quantity. We'll enter scalar quantity. But current has direction. Still it's a scalar quantity because of law of ordinary algebra is used to add electric currents. That is, look, one current is going 2, right? 2 ampere, 3 ampere. We just add and subtract using ordinary algebra. We don't use vector algebra. That's the only reason we are telling electric current. Current has direction. So really this is called a tensor quantity, but this is not there in your book, but it's called tensor. Just for a general knowledge. And loss of vector addition is not possible. That's why we call it what? Scalar quantity. Now what is 1 ampere? 1 ampere is equal to 1 coulomb per second. So 1 ampere can be 1 ampere can be defined. Look, 1 ampere is defined at many places in your textbook. You can define 1 ampere as what? Yes. When 1 coulomb charge flow through an area of cross section in 1 second, 1 ampere current is 1 ampere current is told to be flown through it. This one. Next one is given in your magnetism and moving charges chapter. What is it? Yeah, it is 1 ampere current is the current that is in two parallel rods which is separated by 1 meter distance, and all it's given in that book. So you can use it accordingly. They are asking question, you should answer it. Yes. Okay. Now Ohm's law. Ohm's law, the basic law that we learn in current electricity. Ohm's law. Ohm's law is telling that the current flowing through a conductor is directly proportional to the potential difference. The current flowing through a conductor directly proportional to the potential difference applied across its ends. Across its ends, provided that the temperature and pressure and other physical conditions remain unchanged. So what is Ohm's law? It is telling that I is directly proportional to the potential difference applied across its ends, provided that the temperature and other physical quantities remain unchanged. That is, I is proportional to V. So we can write what? Sorry, we will write it like this. V is directly proportional to I. So V can be V is equal to KR. This KR like KI. This K is equal to R. That is resistance of the conductor. Hence, Ohm's law gives us the equation V equal to IR. Important. Okay. Important means this and all you are learning it for a long time. Yes. Next one is the Ohm's law is only applicable that when the temperature is kept constant. Okay. So now what is ohmic resistors? Ohmic resistors obeying Ohm's law. Resistors obeying Ohm's law. They are called ohmic resistors. For ohmic resistor, let us take okay, this is I. 1 second, something is happening to the device. Yes, V equal to IR we wrote, right? Okay, now let us write about ohmic resistors. It went off. Resistors, they are called what? They are resistors obeying Ohm's law. Resistors obeying Ohm's law. Look, all the resistors don't obey Ohm's law because Ohm's law is very constrained. Everything cannot obey it. Look, something is happening to the device. 1 second. Sorry. Resistors obeying Ohm's law. So VI graph for ohmic resistors. VI graph. We can draw it like this. This is a VI graph. This IV. It will be a straight line. That is, as V increases, I increases. Directly proportional. Yes. Now we have what? Resistance. We are going to define resistance. The resistance of a conductor is the property by virtue, that is the property by virtue of which it opposes the flow of oh my god, one second, by which it opposes the flow of charges through it, or resistance is the obstruction offered by the conductor to the charges flowing through it. Anything is possible. Okay. Yes. Now. Okay. That's over. We know how to write it and all. V equal to IR, etc., etc., etc. Now what is SI unit? SI unit of it? It is ohm. So the resistance of a conductor is said to be, now we are going to define 1 ohm. What? 1 ohm is the resistance of the conductor when the resistance of a conductor when 1 ampere current flows through it and potential difference across the ends is 1 ohm. Is 1 ohm. Okay. Yes, something is happening to the device, that's the reason. And any device having resistance is called resistor. Okay, that's no needed. Now factors affecting resistance. Resistance. One is the my god. Okay, at constant the temperature, what does resistance depends on? One is length, because look, resistance is directly proportional to length. If the length of the wire increases, resistance increases. Reason is that if length of the wire increases, current will take longer time to reach the other end, right? So there are more clashes in between. So R is directly proportional to L. Second one is area. Look, as area increases, the number of collisions is less. So R is inversely proportional to area. Now third one. Third one is material. That is R is directly proportional to L by A, that we know. So R is equal to some KL by A. You can write it like this, right? Yes. This K is given as rho. That's called as resistivity or specific resistance. This is the nature. This shows us the nature of material. That the thing is that this is like what? A refractive index or another quantities like what? What will tell? refractive index or or dielectric constant. Is what it is? Constant for different medium. That's the thing. So at a constant temperature, length, area, and the specific index, specific resistance of the material are important to be noted. Now we are going to talk more on resistivity. That is rho. How to define resistivity? So you know that resistance is equal to rho L by A. If L equal to 1 and A equal to 1 meter square and L equal to 1 meter, then rho equal to R. So we can define rho as resistivity is the resistance of a conductor having conductor of that material, specific material, okay, of that material having unit length and unit area of cross section. Now what is the SI unit? SI section. Okay. Now SI unit is ohm, not ohm per meter, ohm meter. Why it is ohm meter? Look, R equal to rho L by A. So rho equal to R meter square by L is meter. Cut rho, right? Like that it became rho meter. SI unit, rho meter. Now current density. The next thing is current density. Current density is the one second, let me take the definition. Current density is the current density at any point inside a conductor is defined as the amount of charge flowing per second. It is the current density of any material inside a conductor is defined spelling is DE, defined as the amount of charge flowing per second through a unit area held normal to the direction of flow of charge at that point. So nothing. Current density is equal to what? It is the current density at any point inside the conductor is defined as the amount of charge per unit time. The amount of charge flowing per second through a unit area held normal to the direction of flow of current or flow of charge. That is J. We represent J is equal to I by A. A. Got it? Yes. That is current density. Okay. Now let us talk about the flow of charge in external electric field. Okay, you know that MA is equal to what? F is equal to QE. Okay, therefore MA is equal to, here Q inside a conductor is minus E, right, into E. Therefore A can be written as minus EE by M. So the acceleration of the electron when an external field is produced inside a conductor is given as A equal to minus EE by M. So as electrons accelerate, they frequently collide with the positive metal ions and other electrons of the metal. So what happens that as electrons are accelerating, they for sure collide with the other electrons and the metal surfaces, right? And E gains a velocity component in addition to the random velocity direction, etc. happens. So what happens? Yes, there are different things. What happens? Yes, for sure there is a velocity produced. That is if an electron having a random thermal velocity u1 accelerates for time t1, then v1 is equal to u1 plus at tau. I will write t1 to vn. How many electrons are there for till then? un plus a tn. The average velocity, one second, the average velocity Vd of all n electrons, then what would be the average velocity? Add all velocity and divided by n. So that is Vd is equal to u1. We are substituting the equation, plus t1 plus u2 plus a t2 to un plus a tn by n. So Vd is equal to u1 plus u2 plus 2un by n plus a t1 plus t2 plus etc. by n. Got it? You know that initial velocity is 0. So Vd is equal to what? This will be 0 plus a tau. This tau is called as, this capital tau is equal to what? It is t1 plus t2 plus etc. by n. So let us define this tau. Tau is called as what? Relaxation time. relaxation time, that is average time elapsed between two successive collisions. Same collisions. Time between two successive collisions of electron. Yes. So that's about tau or relaxation time. So therefore we found it out that velocity is equal to a into tau. Therefore we can write a is equal to minus e by m into tau. So this will be the drift velocity of the electron. E tau by m. This will be the drift velocity of the electron. Got it? Yes. So this derivation for drift velocity, please learn it. Yes. So what is drift velocity? Drift velocity is the average velocity attained by free electrons of a conductor in the opposite direction. Look, drift velocity is the average velocity attained by free electrons of a conductor in the opposite direction of the externally applied electric field, of the externally applied electric field. Yes, this is it. This is what is average velocity. One second. So now we are going to speak about relation between current and drift velocity. That is, take an area. Imagine this is a part of the conductor having length L. It is connected to an external battery of potential difference. I is the current passing. A is area, electric field inside. Suppose a potential difference is applied across a conductor. We are already applying it. So E can be written as what? This V by L. E can be written as V by L. Right? Okay, perfect. Now number of electrons flowing through that part can be taken as what? N. Charge on each electron is equal to what? E. Number of electrons in L is equal to what? NEL, N into volume of the conductor, N into volume of the conductor. Okay, so what is the volume of the conductor? Length into area A. So NAL is equal to number of electrons. Then next one, total charge, that is Q, that is equal to E into the total number of electron, NAL. So ENAL. Now what we can write? Yes, now we can write time is equal to what? Time is equal to length by velocity, distance by velocity, that's equal to L by velocity. That's enough. Okay, now you know that I is equal to Q by T. So I can be written as Q is equal to what? ENAL by VD. So no, not VD, sorry, L by VD. LL cancels. Therefore I is equal to NAE VD. Very important relation between current and drift velocity. Okay, we can also write this in another way, that is, you know, I equal to NAE VD. A I am taking here, so it becomes I by A NEVD. In fact, I by A is called what? Current density J. Therefore J is equal to NEVD. Just note it. Okay, now we are going to do another important thing, that is deduction of Ohm's law, deduction or derivation of Ohm's law. So we are going to derive Ohm's law with velocity, what? Drift velocity and all. Drift velocity is equal to what? EE by M into tau. That is EE by M into tau. You know that E is equal to V by L. So substitute it. EV by ML into tau. Therefore I is equal to VD into NEA. This is an equation that we got. Now substitute all the values. I is equal to VD. Instead of VD, we will write EVT by ML into ENA. So therefore I is equal to E square NVA tau by ML. Okay, perfect. Now I want to write I is equal to V by R. So V by R equal to E square NVA tau, that is relaxation time, by ML. V cancel. Therefore R equal to ML by E square A tau. I can write this thing I can write as R equal to M by E square tau into L by A. Look, this thing is a constant. Hence okay, 1 second. Sorry, 1 second. I did something wrong. So we should derive Ohm's law, right? I derived resistance. 1 second. one second. Sorry, 1 second. You know I is equal to E square V tau NA by ML. This thing we got, right? Take this V down. So we get, take this V down and take the recipe. That is V by I is equal to what? ML by E square tau NA. Right? So you know that V by I. What is V by I? Yes, V by I is a constant. So this should be this is a constant. It's a constant. Therefore, V by I is equal to constant. Hence, R is equal to ML by E square tau NA. This is what we derive. That is resistance. From this resistance equation, we get also resistivity. R is equal to M by E square tau N into L by A. Look, rho L by A. This is similar to rho L by A. Therefore, rho is equal to M NE square tau. Got it? Yes. Hence we derive that also. Okay. So from here we get to know that resistivity depends on one, electron density of conductor. 2, relaxation time. Electron density of conductor and relaxation time are the two factors that resistivity depends on. Electron density and relaxation time. Okay. Yes. Now another relation, that is relation between J, rho and E. J, rho and E. It's very simple. You know that VD is equal to what? Minus EE tau by M. Yes, and one fact is that J is equal to NEVD that we derived before, right? NEVD. Substitute NE is equal to minus E, that is electron, right? VD EE tau by M, minus E tau by M. Therefore, J equal to NE square E tau by M. NE square E. This I want to write it as J equal to NE square tau by M into E. This thing I have seen somewhere. This is equal to 1 by rho, right? 1 by rho. So 1 by rho is this. You know that 1 by rho is equal to what? Sigma. This is conductivity. Therefore, J equal to sigma times E. This is the relation. Or you take this thing to other side, it will become 1 by rho, 1 by sigma, that is E is equal to sigma J. It's also possible. Understood? Yes. Okay. Now we come to another idea, that is mobility. What is mobility? Mobility of a charge carrier of a charge carrier, carried alla carrier, is the drift velocity acquired by it in a unit electric field. That is mu equal to Vd by E. That is, this is meter per second unit. This is having a unit Newton per Coulomb. That's equal to what? MC by NS. Okay. So really, this is the what only the symbol. So mu is equal to what? This Vd by E. That is QE tau by M by E. Therefore, mobility is equal to Q tau by M. Q tau by M. Got it? Yes. That's about it. Yes. Now let us discuss limitations of Ohm's law. One, for large currents, Ohm's law is invalid. The problem is that when current increases, there is heat generated. That is, heat is lost due to current. That is I square RT. The problem is that this I square RT increases the temperature of the conductor. Hence, resistance also what? Increases. Resistance also increases. Right? Yes. So that's the thing. So, for large currents, Ohm's law, I forgot, right? Law is invalid. Let me draw. This is VI graph. It will be like this. Till here it is valid. After that it is becoming invalid. Okay. Yes. Now, next problem is that if we reverse the direction of V, that is voltage, keeping its magnitude fixed, then magnitude fixed does not produce a current of same magnitude. Because then V should be equal to IR, right? So V should be directly proportional to R. Here and other way it's happening. If you reverse voltage, we are not getting the same current at the same pace. Okay? Does not produce one second. Does not produce a current of the same magnitude as I in the opposite direction. Example, diodes. Diodes. What happens? Yes, look. Yes, it's a graph for the same. Look, as V is increasing, but the problem is that as we decrease it, it should be going the same way, but it is going what? It's going in another way. That's the thing they are telling. That's the thing they are telling. Yes. So this is the figure. This is the figure. Got it? Yes. Yes, this is the second condition. Now third problem is the relation between V and I is not unique. That there is more than one value of V for same current I. In gallium arsenide, the problem is that for one V itself there are two values of I. Not like that. The problem is that there is more than one value of V for the same current I. That is, look, it is going like this, it is going like this, going like this. This is for gallium arsenide. The problem is that here we are having one. Once again at this point, the current is same, but voltage is different. This is the one reason. That is, V and I are not unique. That there is more than one value of V for the same current I. So the three things are: one, at high temperatures due to heat loss, high current, high heat loss, that leads to depletion of Ohm's law. Second one is in case when we reverse the voltage, the magnitude of current is not constant, it changes. And the last one is that V is not unique for I. That is, for the same current I, there are two voltages possible in gallium arsenide. Gallium arsenide. So now we move on to resistivity of various metals. So now we are going to tell about various resistivity for various materials, how it is changing. VT for various materials. The materials are classified as conductors, semiconductors and insulators depending on their resistivities. We know in an increasing order of their value, metals have the value of resistivity 10 raised to minus 8 ohm meter to 10 raised to minus 6. This is very less. That's the reason resistivity of metals are less, therefore high conductance. Another kind of insulators like ceramic, rubber, plastic and all have resistivity. For ceramic or insulators, the range of what resistivity is 10 raised to 18. 10 raised to 18 times greater than metals. That is approximately 10 raised to 10. 10 raised to 10. Right? 10 raised to 18 times greater. Right? So approximately 10 raised to 10. In between, for semiconductors in between insulators and conductors. Okay. Yes. However, we have resistivities carried by resistivity of a semiconductor can be decreased by adding small amount of suitable impurities. The last feature is exploited in use of semiconductor for electronic devices. So they are telling the resistivity of semiconductors can be changed. The thing is that semiconductors, if we add impurities to semiconductor, its resistivity changes, decreases. That is what intrinsic and extrinsic semiconductors that we will be learning in semiconductors chapter. extrinsic semiconductors, that is doped semiconductors. They have comparatively lesser what resistivity compared to normal semiconductors. Okay, understood? Yes. 1 second. Yes. Now we have the next part, that is temperature dependence temperature dependence of resistance. How does temperature depend the value of resistivity? You know that what do you know? Temperature depend, you know that rho is equal to m by ne square tau, right? That we derived. So in metals rho is inversely proportional to tau. Tau is relaxation time. You know that as temperature increases, collisions will be faster. As temperature increases, tau decreases. Therefore, what happens? Rho increases. That's the thing. As temperature increases for a conductor, what happens? Yes, conductor resistivity increases. That's dangerous. So it exploits the character of conductivity of these metals. Now therefore the resistivity rho at a time t, not a time, at a temperature. So if you need to find the rho at the specific temperature T, that's a formula, that is rho naught, that is rho at the room temperature into 1 plus alpha delta T, change in temperature. Okay, yes. Where rho naught is what? Rho naught is a resistivity This is rho naught is resistivity. Now we will be writing it in more specified way, so it's easy to tell. So delta T means T final minus T initial. Okay. So this rho naught is resistivity at T naught, and alpha is the coefficient of resistance. Temperature coefficient of resistance. Okay. Yes. Temperature coefficient of resistance. This rho, you know, this rho, not rho naught, alpha. It is same as what you have learned in the chapter mechanical properties of fluids and solids. Solids, you know, in thermal expansion chapter you have learned what L equal to L plus L alpha delta T. That alpha is what? Coefficient of linear expansion. Like that here also alpha is coefficient of temperature dependence of resistance. Okay. So this is the thing. Now this is very important, this part. For metals this temperature coefficient alpha is positive. For metals alpha, for semiconductors it is negative. That means for semiconductors, as temperature increases, what happens? Resistivity decreases. So in the devices where high temperature is there, high current is used, we specially use semiconductor because resistivity decreases. Okay. Now I'm asking you something. There's a question for practical physics also. Why Maganin and Constantin used for making resistors, standard resistances. Standard resistance. Reason is what? They have high resistivity. So if they have high resistivity, high resistance to small temperature coefficient, so there is no change in temperature. And not affected by atmospheric conditions. Not affected by atmospheric conditions. Yes, high melting point. So these much things we told. Now we are going to talk about variation of resistivity for another material. Resistivity of nichrome wire with temperature. Nichrome wire with the temperature. Nichrome wire is a special type of material that is used in heating devices. What happens in nichrome wire is that as temperature increases, what happens? As an alloy, nichrome has weak dependence on temperature, while that of manganese is independent of temperature. For nichrome wire also, for a high temperature difference, that is 200 to 800 Kelvin, only 0.1 what increases, resistance increases. So nichrome wire is also having a low alpha. Okay, that means that nichrome wire, manganese constant, etc. doesn't depend much on temperature. That way this is used in heating elements. The thing is that it is having a specific resistance. If it heated also, nothing is going to happen to it. Okay. Now we will also draw a graph for semiconductor, that is semiconductor. Temperature rho. This is inversely proportional. This is a graph for semiconductor. Now we go to main part. Not main part, one of the most important part in the chapter, that is electric power. The definition of electric power is important. The rate at which work is done, rate at which work is done by a source of EMF. It's a battery. That's a battery. Source of EMF in maintaining the electric current. Electric current through a circuit. The rate at which what happens? Work is done by a source of EMF in maintaining electric current through a circuit is called electric power of the circuit. Got it? Yes. That is W is equal to VIT. P is equal to W by T. So therefore, what is power? Once again, the rate at which the work is done. by a source of EMF in maintaining the electric current throughout the circuit. So VI, therefore P is equal to VI, or P is equal to I square RT, I square R, or P is equal to V square by R. These are the three equations for electric power. SI unit is what? Unit? Simple. Watt. And one important unit is horsepower. 1 horsepower is equal to 746 watt. Okay, yes. Now electrical energy. It is not same as power, because energy means work, right? The total work done by a source of EMF, it is the total work. The other one is the rate of change of work, right? The rate at which work is done. Here it's the total work done. Total work done by the source of EMF in maintaining an electric current in a circuit for a given time is called electrical energy. Okay, V is equal to PT. P is power into time, that is VIT. It's not Vellore Institute of Technology. And I square RT, these are very famous. This is also heating. SI unit is what? Joule. That's works. SI unit is joule. Commercial unit is kilowatt. Commercial unit kilowatt hour. 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joule. Okay. These are the things told here. Now, application of heating effect of current. Why we use the heating effect? That is electrical heating effect of current. Application of heating effect of current. One is incandescent lamps. That is normal electric bulbs. Incandescent electric bulb. What is happening? It consists of a filament of fine metallic wire enclosed in a glass bulb filled with chemical. Thing is that this is our bulb. Here we are having what? A filament like this. The filament should have this filament should have high resistivity and high melting point. Otherwise it will melt, right? So high melting point. When current is passed through the filament, it gets heated to a high temperature. And it will glow. Because of that high temperature, it will glow and emits light. And the thing you should notice that, yes, so this is about a bulb. The thing is that in this bulb also a lot of energy is converted to heat, about heat energy, but only a small percentage of it is appearing as light. So the light we see in the bulbs is just a small part of the electricity provided to it, very less part. Okay, that's, I'm just telling a fact. Now second one is high voltage power transmission. High voltage power transmission. The thing is that, look, this is a transformer. Step up transformer. This transformer bring current to us using what? High voltage. This high voltage lines. The problem is that these lines, what? Lost lot much current as what? Heat. This is an example of heat current. So electric power is transmitted from one power station to another, factory, home, etc., right? But these cables have high resistance power. These cables usually have high resistance. Hence, what power is wasted in them as heat. Suppose P is delivered to the load resistance. Lot much power is wasted. Really, lot much power is wasted. They are telling that, look. Suppose you think P is delivered, the normal power, the original power delivered to load resistance, that is the starting resistance or the first resistance is RT. P is equal to VI. This resistance is RT. Power wasted in transmission is equal to PT equal to I square RT. I square means P square by V square RT. So this much power is lost. So hence, to minimize the power loss, what should we do? To minimize power loss, we should use what? Use high voltage transmission. As voltage increases, power loss decreases. Use high voltage transmission lines. That is why the transmission lines and all we see in the what? Not in the normal lines commuter home. The big lines that is carrying the lot much power is what? They are high voltage transmission. If you go and keep, it's very, if you stand below it itself, you can have many problems in your life. Like, it's not good for us. That's because it's high voltage transmission line. That's why we use it. Now, third one, power loss in a conductor of resistance R. You know that what is power? It is the rate of doing work in maintaining the electric current throughout the circuit, right? Here what happens is heat is produced in the resistor R, which is connected across the terminals of a cell. The energy dissipated in the resistor R comes from the chemical energy of the electrolyte. Nothing. Look, take an electrolyte. Heat is produced in the resistor R. That is, this is the electrolyte. I have a resistor here. Okay. Resistor R is here. Okay. The heat is produced in this resistor R, which is connected across the terminals of a cell. The energy dissipated in the resistor R comes from the chemical energy of this one. Comes from the chemical energy of the electrolyte. That's what told. Nothing normal. Heat is also dissipated in what? A cell. Here the heat dissipated is what? It's coming from the chemical energy of the electrolyte. That's what told here. That's it. Nothing else. Next one. It is about cells, EMF and internal resistance. What is a cell? It is a simple device to maintain a steady current in an electric circuit. It's a simple device to maintain current in an electric circuit. That's it, nothing else. Internal resistance. It is the resistance offered by the electrolyte of a cell to the flow of current between its electrode. The resistance offered by the electrolyte of a cell to the flow of current between the electrodes. It is called the internal resistance of a cell. These things I know you have learned, so that way no need of more explanation. Now factors which internal resistance depends on is distance between the electrodes, nature of electrolyte, right? 2. Distance between the electrodes, concentration of the electrolyte, right? Inversely proportional to these are not directly proportional, this is inversely proportional to area of electrode electrodes that is immersed in the liquid. That's important. Electrolyte increases with decrease in temperature. Of electrolyte. So these are the 5 factors depending on the internal resistance. Now we are going to look at how these quantities are important. Okay. Yes, so this is a cell. Yes, this is the internal resistance small r. So this is the total cell. This is the cell I R resistance. Okay. Here E is equal to V plus V dash. By Ohm's law, V is equal to what? I R. V dash is equal to what? I into small r. Okay. So total E is equal to what? I into R plus R. Right? Yes. Hence the current in the circuit is I equal to E by R plus R. Now what is the potential drop? What is the potential drop? It is the what is it? Potential drop. The potential drop across the terminals of a cell when a current is being drawn from it is called the terminal potential difference. That is, it is the potential difference across the electrodes when the current is drawn from it. That is V equal to E minus V dash. This is V is equal to E minus V dash I into small r. Therefore, terminal potential difference is equal to one second. Okay, therefore, terminal potential difference is equal to what? EMF minus potential drop across internal resistance. That is E minus IR. This is potential drop across internal resistance. This is terminal potential drop. You know that small r is equal to E minus V by I from the above equation. Right? This can be written as E minus V by R. That is, R can be written as E minus V by V into R. Right? So R can be written as into R. We already wrote. Now some cases, that is, when the cell is open, what happens? V open. When the cell is open, no current is drawn. So therefore V open means it is equal to EMF itself. There is no potential drop because no current. Right? Now a real cell has always some internal resistance. Always a cell has internal resistance. That's truth. Always a cell has. Never the terminal potential difference will be equal to the EMF for a practical cell. Always a cell has internal resistance. A real cell, in possible cases we can take. Therefore always V will be less than, E will be greater than V. Now these are the basics of EV and all. Now we are going to speak about the important thing, that is combination of cells. One second. There we have series, parallel, as we did in capacitor, we have to derive this also. So this is the most important part of the derivation. That is one series combination. Okay, one second. Yes. Combination. Okay. So here is equal to, we'll write it like this. Here this is R1, E1, E2, R2. Okay. Let VA, VB and VC be the potential at A, B and C. At A, B and C. VAB is equal to VA minus VB. That's equal to E1 minus I R1. Now VBC, that's equal to terminal voltage across E2. VBC, that's equal to VB minus VC. That's equal to E2 minus IR2. Now VAC, that is VA minus VC. It can be written as VA minus VB plus VB minus VC. Right? VA minus VB. E1 minus IR1 plus E2 minus IR2. That's equal to E1 plus E2 minus I R1 plus R2. From this equation, this is similar to what? E equivalent plus I minus I R equivalent. From here E equivalent is equal to E1 plus E2 and R equivalent is R1 plus R2. Okay, this is the derivation of series, cells in series. Simple. Now cells in, this is cell in series combination. Now to parallel combination. One second. Parallel combination. Why is this very untidy? One second, let me change it. Okay. I1, I2, I1, I2, B1, B2, A, C. So this is the parallel connection. Now what we will be doing? You know that total current of the circuit is what? I1 plus I2, right? Yes. Now I can write voltage across this B1 and B2 as what? Yes, that is VB1 minus VB2. Look, I can write this VB1 minus VB2. There are two margins. I can write it across both. So if I am writing it as the first one, I can write it as E1 minus I1 R. There is an R1 internal resistance. Here there is R2 internal resistance. Stop. I1 R1. If I am taking it across B2 also, I get the same. So E2 minus I2 R2. From here, what we can write? Yeah, we can from this we will give it as 1 and 2. I am taking 1. What from V is equal to E1 minus I1 R1. 1. Now from here I1 is equal to what? I1 is equal to E1 minus V by R1. And from 2 what we get? I2 is equal to E2 minus V by R2. You know that I is equal to I1 plus I2. Therefore I is equal to E1 minus V by R1 plus E2 minus V by R2. 2 minus V by R2. That's equal to E1 by R1 plus E2 by R2 minus V. We are taking it common. V yes, 1 by R1 plus 1 by R2. R1 plus 1 by R2. Hence V is given as E1 R2 plus E2 R1 by R1 plus R2. One second. Sorry, one second. I'll once again rearrange this. It will be confusing for you, I think. Okay, we got this. We have to make it in the terms of this equation. V is equal to E minus IR. Then only we get it easily. So take I here and take V there. So V is equal to what? E1 plus E2 by R1 plus by R2. We'll take I here. Minus I by this 1 by R1 plus 1 by R2. Okay, yes. So from here we get it as V equal to E1 by R1 plus E2 by R2 by R1 by R1 plus 1 by R2. It's not R square R2. 1 by R2 minus I into 1 by R1 plus 1 by R2. Therefore, from this equation E equivalent is equal to what? E1 by R1 plus E2 by R2 by 1 by R1 plus 1 by R2, and R equivalent is equal to 1 by R1 plus 1 by R2. Got it? Yes. So this is the equation. Yes. So next we have Kirchhoff's law. Kirchhoff's law. So now our chapter is approaching its end. That is, now we are only having one more topic. That is what, after Kirchhoff's law we are only having Wheatstone bridge. So Kirchhoff rules. One second. Yes, Kirchhoff is having two rules. One is loop rule and one is junction rule. First law or junction rule. It is telling that, what is it telling is that in an electric circuit the algebraic sum of current at any junction is 0. That is, or sum of currents entering a junction is equal to sum of current leaving that junction. That is, sigma is in a junction is 0. Okay, yes. This is very simple. Now the second rule is Kirchhoff's second law or loop rule. This is one of the confusing and the toughest part considered by many children in what? Current electricity. What is the statement is that around a closed loop, around any closed loop of network, so the loop of a network, I'll read from NCRT, one second. Loop rule. The algebraic sum of changes in the potential around any closed loop of network, the algebraic sum of changes in potential involving resistors and cells. Inductors is not counted at all. Involving resistors and cells is 0. That is, once again I am telling, around the change of potential around any closed loop of network involving resistors and cells is 0. Cells is 0. That's loop rule. Okay, got it. Now this loop rule is having something called as the sign convention. It's very simple. Look, I will just explain it through an example. EMF1, EMF2, going like this. This is I. This is I1. Okay, one second. This is I. This is I1. I1 plus I. So I am first of all taking one of the loop. I am taking this loop. This loop you consider I am taking. I am taking this loop. Okay, when I am considering this loop, what's happening is that they told that in a loop, inside a loop always what change in potential is 0. So we are equating it. We are equating the change in potential. That is Yes. So what we will be doing? Yes, we are taking a consideration. So I am going to travel in which direction? Mostly, always you travel in which direction? In clockwise direction. Okay, I am going to travel in clockwise direction. So I am going to start from this E3. Look, E3. So I am going to start from here. I am going to walk from A to B, then to C and D. I am starting walking from A. So this side. First of all, when I am walking from A, I saw a resistor R. The thing is that the current is going as the same way that we are moving. Current is going in the same way as we are moving, right? Sorry. So I am telling, okay. Now I am traveling from. Sure, something happened. From A to B. So first I saw a resistor. Look, current is going like this, and we are also traveling like this. If we are traveling along the same direction as the current through a resistor, only through a resistor, this case is there. If the current through the resistor and we are traveling through the same direction, then it will be becoming minus IR. We will take it as minus. The reason is that you know that current travel from, this is positive to negative. Current travel only from positive to negative terminal. For resistor also positive to negative terminal. Here what is happening? From a high positive value, it's decreasing to a minus value. The voltage is decreasing. So plus to minus means what? It's a decrease. That way minus IR. Now we reached this E3 resistor. E3 resistor, from minus to positive we are jumping. So it's an increase. Therefore we add plus E3. Now when I is going, now we reached here. Now we went through E2. E2 means what's happening? Yeah. Positive to negative, gradual drop. So minus E2. This is equal to, no more resistor is there, go to 0. So this is our Kirchhoff law sign convention. Now if you are having another resistor like this R, and I am going to traverse it like this, anti-clockwise, this top part. Only through this resistor I am telling, resistor plus minus. The direction of current through this resistor is like this, that is minus to plus. We are traveling opposite to it, then plus IR, right? So here what's happening, we are traveling like this, minus to plus, so plus E1. Now we came here what's happening, plus to minus, so therefore minus E2. Hence we got the answer, this is equal to 0. So you can do it very simply. Just think, if it's going from positive to negative, give the sign what? Minus. If it's going from negative to positive, give the sign plus. That's it. Okay, this is about Kirchhoff's loop rule. Now two loop rules come to an end. Now 1 second. Now we have something went off. 1 second. Now we have a special condition of what? Loop rule. Special application of loop rule, that is Wheatstone bridge. It is an arrangement of 4 resistors used to determine these resistors quickly and accurately in terms of remaining 3 resistors. If you are keeping 4 resistors like this, 4 resistors P, R, P, Q, R and S. Now I am connecting a galvanometer here. If no current passes through this galvanometer, then this Wheatstone bridge is told to be in a balanced condition. We will come to that. Here what's happening, and we are connecting this to what? External cell, okay, of voltage EMF E. Okay. So now first of all, this is A, this is B. So a current from here I is coming up, and here it is splitting to I1 and I2. Now I1 is going here it is going as IG, and this is becoming I1 minus IG. Here it is becoming I2 plus IG. Here it is once again becoming I. So we are going to apply what? Loop rule inside this. In this 2 loops. This is 1 loop, this one, 1 second. This 1 loop and this 1 loop. We are going to apply Kirchhoff's law. Okay. So taking this loop, first loop, what we can write? Yeah, I am going to travel from A to A A, this point, then this point. I'm going to travel through this triangle. First I am going through this way. I am going as this way. So what happened? I am applying Kirchhoff's law. I am going like this, I1 into P. I1 into P. So that is, I am going the same direction of the current. So that becomes minus I1P. Now, because it's positive negative decrease is happening, right? Now I am going from Q to from this point, this top point to this down point through this galvanometer. So this galvanometer has a resistance G that you have did in practical physics, right? So Ig is the current passing through it, Ig, and the current is going like this, and I am also going like the same direction. So minus Ig into G. Now I am coming here and I am going like this. So opposite current here, just according to this current here is positive minus. I am going from minus to plus, increase. So plus I2R. This is equal to 0. So this is the Kirchhoff loop rule for this first loop. Now for the second loop, I am starting from B and I will come back to B like this, a triangle. I am starting from B and I am going. Now I am going through this S. So I am walking opposite to the current, opposite, plus minus opposite. So increase. So plus I2 plus Ig into S. Now I am going from here to here, from down of this galvanometer to top. I am walking against galvanometer. So plus Ig into G. Now I am coming from Q to B back. I am traveling at the same direction as I1 minus Ig. So minus I1 minus Ig into what? Q into Q. That's equal to 0. This is the loop rule for the next one. Q is equal to 0. We got loop rule for both. And if you solve this, you will get the resistances. But Wheatstone bridge we use in a special condition called balanced condition. This condition is that if we keep this resistance in specific order, that is a specific order, if we keep this resistance according to a specific theory or a specific order, what happens? We get a balanced condition where no current passes through the galvanometer in the middle. No current passes through galvanometer. So Ig can be written as what? 0. Ig can be written as 0. Now I am taking the first equation. That is, Ig can be taken as 0. So I will write it as I2R minus I1P is equal to 0. I2R minus I1P is equal to 0. Now this equation can be written as what? Ig is equal to 0. I2S minus I1Q is equal to 0. I2S minus I1Q is equal to 0. Now I am going to write I2R is equal to I1 into P and I2S is equal to I1 into Q. Right. So I am going to write it now it as I2 by I1. This I can write it as what? I2 by I1 is equal to what? P by R. This I can write it as I2 by I1 is equal to what? Q by S. So these are equal. So I can write it as P by R is equal to Q by S. That is P by R, and if when it becomes equal to Q by S, then the Wheatstone bridge is told to be in what? A balanced condition. Now a question: is this Wheatstone bridge in balanced condition? 5, 10, 10, 5. Is this in a balanced condition? No. Why? Is 10 by 5 equal to 5 by 10? No. That way it's not in balanced condition. If it was 5, 5, 10, 10, then it would have been in balanced condition. Okay, simple. Now the last part of this lesson, or last piece of chunk of the current electricity chapter, that is some advantages of Wheatstone bridge. Okay, first one is, it is a null method. It's a null method, that is internal resistance of cell and the resistance of galvanometer is not independent of resistance of galvanometer and internal resistance. അടുത്തത്, no need to measure current and voltage. There is no measurement of current and voltage, only resistance we know, we keeping it and taking value accordingly. No need to measure current and potential difference, so no intrusion of resistances of ammeter and voltmeter. Ammeter and voltmeter. Okay, one second. Now third one, the unknown resistance can be measured to a very high degree of accuracy. The unknown resistance can be measured to high degree of accuracy by increasing the ratio of resistances in arms P and Q. So these are some advantages of Wheatstone bridge. So by this Wheatstone bridge, our chapter current electricity come to an end. Thank you everyone. Please like, comment, share, subscribe and do everything. Thank you.